Okay. So can I get confirmation that you got a "this is being recorded" message? Any thumbs up?
Yes.
All righty, excellent, thank you. All right, welcome back everyone to day 2 of What's a Microcontroller with Python and the Microbit. So today, Wednesday, we are going to, let's see, am I screen sharing? Yes, good. Okay, today, Wednesday, we are going to be building, testing, and measuring light and push button circuits. And so we will, the lights we'll treat as binary outputs, and then as analog outputs using digital to analog conversion. And we'll also talk a little bit about some programming tricks, as in some of the computer science material that appears throughout the lessons. I know that for the homework, you went through kind of the programming basics of Python. That would be messages to and from the terminal, storing values, making decisions, doing things a certain number of times, and that's pretty much it as far as the homework before the first session. And so this is an example of one of the little pieces that appears that goes into certain computer science topics. Let's see, and then for the push buttons, they are our digital, or our binary rather, input, and we'll end up combining those with things like signal frequency. Oh yeah, that's right. In terms of binary signals, there are things we'll be talking about, like how fast a light turns on and off, and how that is a set of lessons for frequency, the period of a signal, which is the time it takes before it repeats itself, and duty cycle, which is a ratio of high and low times. There will also be a little bit of catch up because I didn't quite make it through everything I planned on Monday. So let's start with that. So this is going to be a little bit of a whirlwind tour. And we also need to start working on unmuting ourselves and saying, "Hey, Andy," because although we do have Ari on the hosting today, I'll be flying solo on Friday, and I'm not very good at checking the chat log. So, so when you find yourself typing something into the chat, after you've typed it, hit the unmute button and say whatever you were typing, and that'll get us all in the habit for Friday.
Hey, Andy, and while we clarify that, can you pass me the host again? It seems that when you came in,
oh, did I take it away?
Yeah, you have it again.
Okay, more. No, participants.
Yeah,
looking for you in the list. Make host. All right, there you go. Oh, yep, there you go.
There we go. Thank you.
Certainly. All right. So set power for circuits is where we almost made it to. And looking at the setting power for circuits, I'd like you all to look carefully at your boards and compare just the power connections. You've got a lot more on there by now than this, but I'd like you to very carefully check and make sure that this red wire here is in E11, and that its other end is right next to the red stripe. We definitely do not want it by the blue stripe. Likewise with, and then the next one to check is to make sure that your black wire up top here is going from a socket by the negative stripe in the left bus strip to a socket by the negative stripe in the center bus strip. And then right below that, we want to take a jumper, also a black wire, also next to the blue line, and go over to the right bus strip and connect next to the blue line there. Then the last one to check is to make sure that your red wire is in one of the red plus sockets here and goes to one of the red plus sockets on the bus strip over on the right. So please double check all that because it's very, very important. And so, yeah, we've even got a little animation where we zoom in on the various connections. So coming back around, it shows where the wires go, and then it zooms in on each of the connections. And this will hopefully help students make sure that they've got their connections all just right. Okay, moving on. The next thing to look at is the parts and circuit. And let's see here. I may have just been here. Ah, yes. So here's another good, well, that is the close-up we were just at. So I think I will continue. All right. So one of the things that I'm going to skip is measuring the voltage of those sockets. But there, just so you know, there is a thing where you go through with the voltage probes and you're measuring voltage and making sure that everything at the everything in these blue stripe sockets measure as 0 volts, and everything in the red stripe sockets measure around 3.3 volts. Okay, and then we talk about how it works, which is going to be helpful for the students to see, you know, hey, these are your 3-volt sockets, and then these are your ground or 0-volt sockets. And we show it as 0 volt and then ground. We talk about a real voltmeter. And then, by the way, this is your whirlwind tour through what we're skipping, because most of this, we're going to focus on a few things in terms of using the cyberscope as a voltmeter and as a signal checker. And by doing that, you'll be able to go through the rest of this with confidence. So we're kind of taking a flight over the forest and looking at the tops of the trees, so to speak. And I will slow down in a while when we start doing some of when we get to the point that I think hands-on is going to be most useful to you for things that you'll definitely want to know, because they apply to all this as well as things following it. All right, so so this is where the cyberscope is introduced. And so I'm going to swing by that for now, because it is step-by-step instructions. And yes, you can follow them, but we're going to do it together as a group later. And one of the things is that we show here that you can measure the voltages in the terminal with the cyberscope, but you can also measure the voltage in a very voltmeter looking interface in the cyberscope. And so that's what this is showing. I guess I'll let it go all the way through because it's pretty instructive. So basically, after you flash the example that you downloaded into the cyberscope, you run over to the cyberscope, click connect, and then set it to voltmeter. And then you'll be able to see the voltage measurements you're taking with a voltmeter style display, like the picture of the voltmeter device that we did earlier. So then we go through and look at, hey, you know, here's a DC light. We're just going to plug it in without even blinking and have it turn on. And we're going to use, you know, parts like a resistor. These parts are introduced in just a little bit. And then likewise with the light, the idea is to first put it together and experience it. And so building the LED circuit is, I think this is pretty cool. So see, watch carefully on the left and right. I'll actually just open this up so we can control the. Okay, so for this one, if you're teaching students how these electrical connections relate to the schematic, I think this is going to be really important, because here we have an empty schematic and an empty breadboard, with the exception of the power connections. And then notice that a wire appeared and a ground connection appeared on the schematic. So we are connecting ground onto the breadboard, and we're showing a ground connection on the schematic. And then the next thing we do is, next part over here is the resistor, and it's going to move over to the breadboard. No, I'm sorry, that's right, the LED. The LED goes first. So here's our little light. And so it moves, it gets plugged into the breadboard, and you can see the little plus here, and that actually corresponds with this little line. It's a one-way valve, and so current can only flow through it one way. If you get it backwards, nothing bad happens, it just won't turn on. And then second to last is plugging one end of the resistor in. So now we have a resistor floating in space, and we have a floating resistor connection on the schematic. And now the resistor is plugged into the 3.3 volt rail here, this column of sockets by the red line. And then we zoom in just to make sure the students have got it wired right. And after that, the idea would be to plug in the USB cable so that the whole thing has power, and verify that the light turns on. Okay, so that's something that we're skipping because we are connecting it to the microbit, which you'll see later. But the idea is that you can plug in USB, the light goes on, you unplug USB, the light turns off. And so that's seeing the connection and disconnection of power. After that, we talk about, okay, this is a light emitting diode. This is what its schematic symbol looks like. This is what its pins look like. And there's a little flat spot right there. Yeah, I think this picture is going to need to be edited. Let's see here. No. Okay, it goes in, here comes, yeah, no, the picture is okay. Sorry about that. And then we introduce the resistor as a part that resists the flow of current so that you don't run too much electricity through your light emitting diode and break it. And then this nice little schematic here is as well coupled as I could make it to the actual physical circuit. And in larger companies, sometimes you will actually see schematics that are drawn to give the technician who's building the actual circuit cues onto how it should be wired. Resistors, you may have noticed, have little stripes on them. And the stripes, the resistor that we're using here has the red, red, brown pattern with a fourth gold stripe. And that gold stripe shows how precise the value is going to be. And the other three stripes, the three colored stripes, are color coded to give you the actual resistance value, which is measured in ohms. And red is 2. So we have red, red, brown, which is 2, 2, and then we add 1, 0 to that for 220. A lot of classes also say 2, 2, or 22 times 10 to the first. So just to keep it simple, I'm just saying, hey, it's the number of zeros to add. And we talk about how current flows through a circuit physically with the electrons going from negative to positive in the battery, whereas in a schematic, it actually is depicted as flowing from the positive to the negative or ground. Then last but not least, we always have the students do something else. And so they have to swap out the resistor and observe that the brightness of the LED went down as a precursor to current. We always put some solved questions, exercises, and projects at the end of any given chapter, along with a few solutions. Okay, and in addition to this, there's another set of questions, exercises, and projects in the educator only area of learn.parallax.com. Some of you have received emails to go there, and also on Friday, we will be looking at that. Most of you have learn.parallax.com educator accounts already, so your homework will be to make sure you've got your password so you can get in. All righty. So that's that. And then some other things. This is the electrical measurements chapter, which is going to be optional for some of you. For the pre-engineering side, it's going to be a pretty important chapter. And so here you can see an example of where we're taking measurements. In this case, these are voltage measurements, which is introduced in the chapter as a form of electrical pressure that propels electrons through a circuit. And when electrons pass through a circuit, we call that current. And then there's also the thing that resists the flow of current, which is called the resistor. And so in this chapter, in addition to measuring voltage, resistance, and current, we also talk about measurement units and Ohm's law. And actually in measuring voltage, we talk about a law called Kirchhoff's law. And in current measurement, we talk about the current form of that, a law named after the same guy. All right. So measuring voltage, you basically put together the same circuit I just talked about. Go back here just so you can see it's the same circuit that was built up before. This is the same actual file. And then what you end up doing is downloading cyberscope.hex. And I will have you do this shortly. I'm just doing a quick, again, overview of some of the things we're skipping over because I want everybody to know that they're there, especially for the pre-engineering folks. And the electronics classes, I want them to know that these are resources. And so the idea here is that you can take measurements like this is across the whole circuit. And now we're measuring only across the resistor. There's a smaller voltage. Then we're measuring only across the light emitting diode. That's also a smaller voltage. And then after that, when we go back and measure the voltage across the entire circuit, it turns out that the voltages of the parts add up to the voltage across the whole thing. And that's something called Kirchhoff's voltage law, which is introduced right here saying, okay, well, if you have a voltage source and you have a resistor, it will have a certain voltage drop, and you have a light, it also will have a certain voltage drop, and you add these two up and it should come up to this. All right, and then there's the end of activity material where we have questions, exercises, and projects about what the students learned and some answers, and we can encourage them. Oh, there's no projects in this particular section. And the idea would be to encourage them to do this, make sure that what they come up with matches the solutions that are provided, and then the summative assessment materials that are in the teacher resources can be used because they're only available to you. And so you can take the similar versions of these and provide them as handouts or as quizzes, tests, however you see to best use them. One thing about measuring voltage that is important to note is that you've got your circuit, it's connected, there's even power in it. This light should actually be having the little glow symbol. And you can have the circuit in there and you can simply probe at different spots and measure the voltage across those parts of the circuit as current is flowing through it. And that's what you get from the voltmeter. Now, when we come to measuring resistance, there's a entirely different rule. So the first thing that we do is build a little extra circuit down where you added your 3-pin headers on Monday. And then what's going to happen here is this resistor right here is going to come out of, I'll just go to the next slide. So basically you build this little extra part of the circuit as your resistance meter. Okay, and then you'll download the script and load it into the microbit, and then you'll be able to measure resistance. And the way resistance is measured is by removing the resistor from the circuit and then probing each end of that resistor. And so that's a very important thing to get across to the students. I have unfortunately met engineering students who have recently graduated from a university, have appeared at a new place on the job, and they're probing the resistor inside the circuit and not understanding why they're getting a resistance measurement that's so wildly different from the expected value of the resistor. And it's because they didn't take it out of the circuit and do exactly what's shown here. So this is a very important lesson for anybody who's going the engineering or technician route, to be able to take a resistor out of a circuit, measure its resistance, and put it back in. Then we talk about how those measurements work. Again, I'm just kind of flying over this, just want you to know that these things are in the lessons. Resistors can also be combined. They can be connected end to end, and they'll have an equivalent resistance when you do that. So for example, these three 220s will just all add up and become 660. They can also be connected basically side by side. And in that case, there's an equation that you use to figure out what the resulting resistance is. In the case of two parallel resistors, two side-by-side resistors, it's half of their resistance if they happen to match. Otherwise, there's this little equation. And these are things that they're purely academic. So I know that, with this and the teacher's guide, and the solved solutions, that you'll be fine with this. So I really want to just make sure to focus on the hands-on stuff. Again, we have questions, exercises, and projects for students to practice, and then the solutions. And there's a similar set that we'll share with you on Friday. Although you all technically have access to it right now. Today, I don't want to pay any attention to it. Measurement units. So we talk about how the K in kilo really means 1,000. And we go through the mathematics so we go through the mathematics of, okay, K is kilo. So we want to replace that with 1,000. So when we say we have 1 kilo ohm, omega having been introduced on our way here as the unit for resistance measurements. So like that 220 ohm resistor, that's the omega for ohm. And so this is the part where students are become familiar with SI units and how to convert actually SI prefixes in this case. The resistance would be an SI unit. Kilo would be a SI System International prefix. And so kilo, 1,000. We also do milli for 1/1000th. And there's some math lessons included in here where we have our little virtual chalkboard GIF image right here. I was corrected during the previous course. I've been calling it GIF all along, and I probably still will. So excuse me in advance if I mispronounce GIF. Now, after doing the math lessons, it kind of begs, well, how about if we write a script to solve that problem and let the microbit do it? And that's what this is about. And so once you've run the script, you can open up the serial terminal, and it'll say enter a quantity, and you can type in 1 and K, and then it'll give you, and then type in whatever follows it, and it'll give you the resulting 1 kilo ohm is 1,000 ohms. So it does the conversion. And then basically we also go the other direction. So converting quantities to prefixes, it's the reverse of it. We say, okay, well, I have 38,000 hertz or 38,000 repetitions per second. Again, I'm going very fast. This is all introduced. And if we had a couple days class, we could go through it at a leisurely pace. But again, just emphasizing, here it is. These are lessons that talk about these science, physics, chemistry, and electronics based topics. And again, we have our little chalkboard to show how to make those conversions. Measuring current is another one where I do want to bring something to your attention. Again, when we measured voltage, you could just probe the circuit as it was built. When we measured resistance, we had to take the resistor out of the circuit. When measuring current, the key thing is that you have to break apart the circuit. This is showing how to add a resistor to make your formerly voltmeter an ammeter. And so then here's the circuit broken apart. And then here is our little ammeter portion inserted into the circuit that we just broke apart. And so the current actually travels through the light, through the ammeter, and then down to ground. And so that's how, so just a heads up to pay very careful attention if you're teaching the measure current, that this is the trickiest part to break, to first of all, add the resistor here that's called out, and then disconnect the circuit from itself, and then insert your ammeter circuit so that current flows in through the circuit and then back out here and to ground. And so that's something it's really important to do hands-on, and there's definitely a MP4 version of the GIF file so that you can do that a little bit at a time, and you can actually open it up and say, okay, well, I see these written instructions, but maybe it'll be easier if I just pause it. Okay, what do I do first? Looks like first I'm inserting that resistor there in those two particular sockets, and then continuing on. Oh, look, the circuit was looking like that, and it just changed to that. So I think I'll, take the wire out of this socket and put it over there. And so that way they have full support in successfully taking the measurement.
Andy, is that a 10 ohm resistor you put in there?
Let's see. I think it's a 20. Red, black,
right?
black. So 2, 0, and then adding 0 zeros.
Okay.
Adding no zeros. Yeah, so that's a 20 ohm resistor.
So does that have to be in there, or?
It does, because basically, by virtue of the fact that some current is going to be flowing through it, the more current flows through it, the higher the voltage across it. And that voltage is measured as the difference between, by the microbit, as the difference between P0 and P2.
Okay.
And so it's not identical to like a magnetic current deflects magnet kind of.
Regular multimeter, I would just pull one lead and stick the meter probes in the series. So
yeah, and you are still, that is true. So you are still doing that here, but yes, this is an extra step for our homemade ammeter.
Okay.
Yeah, and we're using a small resistor instead of magnetic parts because it's less expensive and it does the job to the extent that we're trying to do it. Since you have real meters, you may not be concerned with this. You may have other ways that you prefer to teach it to begin with. But it is available for classrooms that even don't have a lab. The idea is that we're making this available now. Yeah, really good question. Please keep on jumping in, everybody. I want to hear from you. The last part of that is Ohm's law. Doing okay at the half-hour point. Okay, so Ohm's law, I just referred to, actually, we just did it. We're talking about an application of it where the unknown current is equal to the measured voltage over that known 20 ohm resistance. And I is for current, V is for voltage, R is for resistance. And so we take students through some of the facets of this, and it's good for an algebra, anything where you've got a linear equation. If a practical application of that is the goal, well, here is a good avenue to giving the students some hands-on experience from that. And it also is, if the goal is teaching electronics, it also is nice from that standpoint. And again, after studying the math of Ohm's law, we write some code that can calculate, from one unknown and two knowns, you can basically get the unknown value. So in this case, we type in 1.2 for the voltage measurement, and then 220 ohms for the resistance measurement. And then we get 5.54, and students will have had practice with that, the scientific notation and the SI units. And so they will be able to make this conversion to 5.45 milliamps, thousandths of an amp. Let's see, is there anything else to talk about here? All right, so at this point, we're having them solve for one of the other unknowns. But I'd like to call your attention to the fact that this is not typed in. If we go back to the previous page, okay, this is something that students can and undoubtedly will just copy and then paste into their microbit editor. So boom, I'm ready to run this. And that's fine. We know students are going to do that, and we want to leave enough pre-written code. However, you know, for best learning outcomes, the way to do it is to instead put your editor next to your tutorial and actually type all these things in. So
I think we have a question from Rosa.
Oh, Rosa, what can I answer for you?
Yeah, it's not, but is this like a good material to incorporate in like an intro physics or AP physics type of class? What is?
I think it's got some potential. It is pre-engineering electronics material, but certainly AP Physics, it would fit as a module within the class, within the electricity and electronics part. Absolutely. You know, pretty much everything from technician level electricity and electronics pre-engineering, and then the physics, all would be able to use this. And that is one thing, is that we do try to make things that are generally useful. We have a long history of seeing our textbooks and kits used everywhere from junior high school, middle school to a university class. It's just happened that way since we started publishing the material. And so we do try to leave it a little bit open-ended, and we don't say, you know, okay, well, this is for, you know, 11th grade electronics class, and you have to have this equipment. No, we're just making the equipment available as a part of the microbit system that we're making available. Was that a good enough answer? Okay, Rosa, if you have any more comments, just unmute yourself or questions. Otherwise, I will move on. But this particular chapter would be of interest to that group, and it may be skipped by, say, middle school, if especially like a maker kind of situation where you're just plugging in the light and running the first program in a given chapter to make the light blink. Yeah, that's going to be a thing where that teacher might skip this whole chapter because it has math. All right, so that is some stuff that I'm skipping over, and or you know, that we just kind of did a whirlwind tour of, and now we are arriving at the circuit you have built. If I can get back there. Okay, my apologies. I've lost my slides. Here they are. Okay, so next up is connect and blink the light. I think before we start here, I'd like to get just folks' feedback on how far you made it through building the circuit. So I'm going to stop share. Hello, everyone.
You mean like do the homework?
Yes. Yeah. So have we all, how was your success on the homework? Jace's board looks good. Megan, your board looks awesome. Oh, Mike, you guys are rocking it. Look at this, Rosa. That's, I couldn't quite see it because again, you're auto.
Do you see it
There we
now?
go, looking good. Sean, looking good. Jing Chen looks great. And then Norman, excellent. Okay, so I guess we're all ready to go, huh? Okay, let's do
And
this.
it felt like a lot of homework.
I'm sorry?
It felt like a lot of homework.
Yeah, I know.
Considering that we're in the middle of teaching, I just felt like it was fun though.
I'm glad about that. I'll try to scale it back for next for the next session, okay? All right, so let's see here. Share a screen. Now, the first thing we did, now I don't know how many of you went straight from the picture and how many of you went from the activity list I sent. Can I get some thumbs up? How many did the activity list? Went through each of the activities. Okay, so I'm getting, it's looking like about 50, and then thumbs up for how many just built straight from schematic or built straight from the diagram. Okay, so we've got some folks who still are going to need to test their circuits. This won't take long, so that's fine. In that case, let's go ahead and, okay, what just happened here? There we go. Okay, share screen. All right. So in Connect and Blink a Light, don't pull your circuit apart. I think that you will probably have a yellow light connected to P14 instead of the green light shown. That is fine. So script and tests, we've got this little script and you can just go ahead and copy it into the, I need to relaunch the chat. For some reason it closed here. Okay, so in this case, I'll just go ahead and copy that in. So you should be able to take that out of your chat and copy it into python.microbit.org. And then hit connect, choose your COM port, and then flash. And then okay, so I'd like everybody to do that. And while you do, I need to disconnect my, okay, so stop video. Okay, so I'll stop my video. There we go. And then I'll open this guy. There we go. I learned the hard way that having two cameras connected to this particular computer is not so great. So I'm using the camera that I had on me to view this. So this has a little bit more than you've got, but as you can see, it's got the, right now, I've got the, it's very faintly blinking, but hopefully it is visible that the yellow light is blinking. And that's what we, if you look down at it from directly from the top, you'll probably get a little bit better view. How's that look?
Better.
Okay. Excellent. So we're all good with that?
Which light is supposed, I have the blue, the green one blinking.
Okay, so that might mean that you have, do you have 3 lights? Can you hold your,
Yeah. I do.
okay, so look closely and check if your green light is connected to, so the green light should be connected to P13, the yellow to P14, and
Yeah.
the,
Oh, sorry. I just, this was the very last one I did. I had the yellow one on no, on P14, right?
yes, yes.
Okay, so right now, oh, that's weird. It's the green one that's blinking.
Yeah, so it could be that 2 of the resistors are touching each other. Although I'm trying to work out in my mind if that would cause the yellow to blink. I think I'd expect the green to blink in that case. And then the other thing is basically if you have, so like right now, if you follow from P13,
Uh-huh.
see here, my video froze. I'm waiting for it to unfreeze. Okay, here we go. If you follow from P13, make sure that you have a resistor in the P13 row, and then that should go over to a green LED. And then if you run
Okay.
back over and look at P14,
Yeah.
go right from there, there should be a resistor going to the yellow.
You know what problem I have, Andy? I follow the activity list and I left it at the end when we were testing like the voltage and all those things. So I noticed that one had me almost like undo the big, my apologies. I'll quickly put it back
Okay.
as it was before.
You have gone through this and already succeeded. So also
yeah,
I'm
I've
not
tested everything. Yeah, and it passed.
Yes. Okay, good. So go ahead and continue with that.
Okay.
So in the
But
lesson,
do you want me to put it like that?
you know
back to
what?
that?
Okay, hold on. I'll take a look at
Okay.
your, I'll take a look at you real quick. Where, which one are you?
Yeah. See,
Okay.
let me
Go
quickly
ahead and
get
put
the
it.
email. See right there. Do you see it?
You know what? That's
What
fine.
I have is I have the see when you send the activities in the homework. I left it right after I did all of them, but the last one I did was measure light with the oscilloscope. So that's the setting that I have. Do you need me to go back and put it?
You know what? Go ahead and leave it for now. Let's just see what happens.
Okay.
And because I think you'll be fine anyway, since you went through those activities. All right, so after the thing where you can just copy and paste a script, the next thing that happens, and this is as universally as possible through the tutorials. Well, I mean, first of all, we explain how it works.
Andy, you may want to share, I think, the screen.
Oh, thank you. Yeah.
There you go.
All right. Alt. Okay, I got to find Zoom. There we go. All right. Sorry about that. Okay, so we started at a page where you could just copy and paste the code. Now, the next page talks about how it works and then challenges the students to extend something from that. So here we have a lot going on in this. It basically shows, first of all, take a look at the code. Notice that a different part of the code gets highlighted for a certain amount of time. Now, if you watch, the next time it comes around and hits right digital 1, the light comes on. And then it sits at sleep 250 for a while. And then it hits right digital 0, the light goes off. And then it stays at 250 or 2500 for a while there. And so this is showing how, pin 14 write digital 1 will turn the light on. Sleep 2500 waits there for a while. Pin 14 write digital 0 turns the light off, and then it waits at the sleep following below it for a while. All of this is indented from while true, so it all happens inside that loop. Additionally, it shows that when the light goes off, for example, the 220 ohm resistor gets connected to ground. When it comes back on, the 220 ohm resistor is connected to 3.3 volts. It also shows that as something that's happening internally inside the microbits microcontroller over here. It's showing that your script is actually causing the connection of that P14 pin to change inside the microbit, that the microbit is doing the connecting and disconnecting for you. I don't know why the MP4 one isn't here. That's very important to have. So I'll make a note to find the MP4 of that, because it's crazy not to have it here. This is the place where we're talking about how it works. So we need to be able to examine it closely. At any rate, that'll get added. So the first page, the student had code that they could just load and run. This page has that same code, but it's been changed. And so it's up to the students to actually take the earlier code and change it. In this case, they're changing this one line to make it blink 10 times as opposed to make it blink indefinitely. Then there is talk about on-off signals and how they are measured in electricity and electronics. So we talk about the period. When something repeats like an on-off signal, it has a certain amount of time it stays on and a certain amount of time it stays off, and that's called the period. The frequency is 1 divided by the period. So if you have a period of half a second, 1 over 0.5 would be a frequency of 2, and the measurement is hertz, or repetitions per second. We also talk about the ratio of time on versus the total on plus off time. And these actually end up mattering later so that they get reused. And so then after the new academic material introduction, we have something called your turn. Now, depending on how big of a jump it is, I either provide a solution for the students to type in, or an assignment with some hints and a solution. In either case, the solution is for you in a hex file or in written code that you can copy and paste from the instructor materials. So in this case, what they're doing is let's try it ourselves. Let's see, LED blink variables rate, and we are in the blink part. Okay, so bear with me a second. That's on-off signals. Okay, so I'm going to show you something. I'm going to paste you a link, and you're going to get the link out of the chat. And then watch very carefully. You'll paste it into your Chrome browser. And it'll basically take you to a screen that says, we can't preview this, but you can download it. And so that's the thing to do, is to download the file. Okay, now once you've downloaded the file, go to your Python editor and drag and drop the file onto your Python editor. And it'll open up. So this is from the teacher materials. And then you can try it out yourself. So let's do that. Okay, get ready. For some reason I lost the chat again. Chat. Paste. Okay, so again, paste that link into a new tab on your Chrome browser, and then download the file. And then go to python.microbit.org and drag the file you downloaded into the editor. And then connect Flash and then check the result on your light. Yeah, so video wise, I won't be able to show it to you, but basically it blinks faster and then slower and then faster and slower repeatedly.
Oh, yeah.
Okay, how's it going, everybody? Did you guys get that?
We're good.
All righty. Anybody need me to slow down, or shall we go to the next example? Okay, questions, comments? Just jump in. All right. So again, we have a topic, in this case, connect and blink a light. Then we have a script and some tests. That's just really easy because it's pre-written. You can paste it in. Then we've got a how it works, but in the how it works section, there's also a try this. And it forces the students to put their hands on the keyboard because this is a picture of the solution. It's not the solution itself. Okay. And then there's a deeper introduction where you learn something else. And then in this case, the period and the frequency of a signal. And then in this case, it's applied with a script that changes the period and the frequency of the signal by changing the amount of time, the amount of sleep time between the on and the off event. Okay, so next up is brightness. So we're switching, excuse the pun, from a binary output to a analog output. Although in the end, it turns out to be binary anyway. I'll go ahead and paste you this, just like the students would. And you can go ahead and put that in your python.microbit.org editor. Incidentally, even though I skipped it, harp on your students to make sure to name their script by, taking the name in the script and putting it in the script name, and then having them save a copy using that load save button and downloading the project hex, something we talked about on Monday, but it bears repeating. Now, when you flash this code and then look down at the top of your LED, what we should see is some varying brightnesses. It should go from pretty dim to kind of dim to dim, and then to as bright as it can be. Again, I don't know if my camera can catch that. Yeah, so because of the fact that the brightness is actually a rapid series of on-off signals where the on time is controlled, as we introduced in the previous activity, the camera is not sampling it fast enough so that we can't really see it on my video, but I'm hoping that if you look down at your light, you will see it cycling between 4 distinct brightnesses. Looking good? Or do you need more time? I'm watching the chat, so you can tell me more time or looking good. have one, I'm good. All right, in that case, I'll take silence as assent.
Let me ask you a question.
Yeah,
So essentially what you're doing is you're, when you say you're varying the brightness, you're doing a pulse power on it, on the LED. Is that what you're doing?
yeah,
With
so
with this code right here, you're pulsing it and you're changing the duty cycle of the pulse.
that's correct. So the right analog method, it splits up a high-low signal. The high-low signal lasts for 20 milliseconds.
Can you add the time data to the drive?
I'm sorry?
Oh, sorry, am I not on mute? Sorry.
Oh, okay. You're talking to somebody else. Okay, so right analog causes the IO pin to send an on-off signal 50 times a second. Now, when it says 128, that's 128 10/23, actually 128 10/24 of that 50th of a second, it'll stay on 50 times a second. So it's not something the human eye can actually detect as flashing. The limit for that is, well, it varies with color and intensity, but it's generally accepted to be around 30, a little under 30. Old analog televisions depended on that fact. Then 256 is basically a quarter. So 256 over 10/24 would be 1/4. So it's on 1/4 of the time, again, flashing at 50 times a second. Then 512 is on half the time. And then 10/23 is on almost all the time. There's just a tiny little low time in between each of them.
So
And
you're
that's
saying
how-
that 1023 is a little bit less because it should have been 1028 if it was all. That's something like, or 10 something, 1024. Is that what you're
Yeah,
saying?
it's 10/23, it's on for 10/23 10/24 of the time. And that's a very common thing for both analog to digital and when you're measuring digital to analog. And when you're measuring analog to digital, you get almost the entire full scale, but not quite.
I was just wondering why you're not getting that last bit.
Well, I'm afraid it's going to take too long to talk about that. It's just a standard thing in the way A to D and D to A converters are designed. They're, I mean,
Is that
even
because zero? Is that because zero is counted as a bit?
well, zero is counted as a bit, yes, but it's a little bit deeper architecturally than that. So it's something that I'll have to take it up with you after.
Okay, all right.
Yeah. Okay, so moving on to how it works. Again, there's more material introduced, or well, in this case, how it works is explaining, how the thing works. And then there's a try this. And again, that's where the students get to put their hands on the keyboard. And this one's kind of fun. I'll go ahead and text you this one. Okay, so that is analog. So set brightness, how it works. Does anybody need a repeat of the slideshow, or did you all save that last time? Because you can get these for yourself out of the slideshow afterwards if needed. Okay, so there is the, did I not send that link? Oh, you need a repeat. Gotcha. Okay, so I just sent the link to that code example. Go ahead and try it and you'll see an interesting behavior on the light. It'll be much smoother than the, so what we just did is switched from 4 different brightnesses to 1024 different brightnesses. File, share. Okay, copy link. Okay, here is a repeat on the link to the slideshow. Definitely save that for later. It's not nice to have around. It's a good thing to be able to return to.
Listen, I don't, this might be a little bit, very minor point, but let me ask you a question. I believe what you said was at 256 bits, it was on for 1/4 of the time. Isn't that 1/4 plus 1 bit count 0?
No, because the whole time is 1024 slots.
Okay,
And
okay, so they start counting at 1, or do they start counting at 0?
0.
well, it depends, but I'm not sure it's a good idea to get into this level of minutia during the main
Okay.
presentation. We can save
I
that for,
just wanted to know how many bits were in the byte, that's all.
yeah. Basically, it is as close as possible to 1/4 of the total cycle time on when you're at 256. So if we go back to where that was shown, right here, if we think about there being a total of 1024 slots where you could be on, but you can only fill 1023 of them, and there's always going to be a low blip between the repeats. That the total amount of time on here is 1/4 of the available time. And it is true that we can look more closely, or that some classes will want to look more closely at that. But at this level, at this point in the introduction, we don't have a way of taking a precise a measurement that's quite precise enough to verify whether we're 1 bit off or not. So yeah, just think of 256, or at least at this point in an introduction, I would definitely just be explaining it as 256 1024ths. Okay, so everybody got to try this? I'm going to take silence as assent. Okay, so we talk about D to A converters, because D to A converters are taking integers in this case and giving us a certain level out of it. But if this were analog, if we had a dial we could twist, we might be able to get something more precise. Like instead of 514 to 515, we might be able to get 514.333333 or 514.666666. But with a D to A converter, we start with a digital value. And in a truly continuous analog range, we get certain levels. It's just that the levels are so small that the eye cannot detect a change in level. And we talk about binary numbers and how they're used to count. And let's see here. Oh, and we talk about doing a small test before using large values. So for example, this is a test to say, hey, I'm trying to count from 5 to 0 in steps of -1. Does that really work? And so you can run this little piece of code and see if it works or not. And then after that, you can say, okay, well, let's do for brightness and range and go up to 1023 and then down to 0. And because we did a test earlier with, just 4 or 5, we can be confident that counting all the way from 1023 to 0 in steps of -1 is going to work properly. This also talks about looking it up in the documentation, and there's links there and stuff. So Okay, how are we doing on time? 20 minutes left. So then there's the usual review and practice and solutions. Okay, and so we can add a light, and I'm going to skip over some of that because it is pretty much like a repeat of the building and testing we just did. Let's talk about a little computer science side shoot. So before we do the next application, we talk about lists in Python. Lists are a lot like arrays in C language, basic. They all talk about arrays. In Python, there's a thing called a list, and you can put a whole lot of different things in a list. It doesn't have to. Arrays in other languages, you'd have to stick with this pattern of, yeah, green, yellow, and work, but you can't replace red with 3 in other languages. Well, in Python, you can. And so, so lists get introduced, and then there's a program that does lists, and then it runs you through the different entries of the list. And then what's important, or what I want to draw your attention to here, is that this animation shows, hey, this is, we created a list named CList, and there was CList of 0. Let's see, this one I definitely want to do the, okay. So, so the name of the list is CList, and then green is CList of 0, as in square brackets. So when we see square brackets, I'm going to say of. So it's CList of 0, CList of 1, and CList of 2. So then we set the index value, a new variable, to 0. In Python, you can create variables on the fly, so I didn't need to declare it anywhere. While true is just while true. It means that everything below and indented will be repeated indefinitely. Now, this color of CList, well, we know from line 6 that index is 0, so that's 0. So it's really CList of 0. So that's what gets put in this little slot. And then that gets copied over to a variable named color. Then we print color, and see color appears to be green. Then we sleep for 1,000 milliseconds right here, waiting for a full second. And then index is 0, but lo and behold, we're adding 1 to it right here. So now index stores 1. And so this is a nice thing to show students exactly what's happening inside the variables, and also a way to get across, okay, you know, we have a list called CList. There's a function called len, which gives us the length of CList. And since 1 is not greater than that length, it's false. So we skip over putting the index to 0 and displaying nothing. And then we go back. Well, now index is 1. So CList of 1 sends us to go grab yellow from CList and then copy it into the variable named color. See how this is presenting how the code is working out? Does that seem like it's going to be a useful teaching tool for getting across that idea of that computer science idea of lists? Let's see here, share screen. Oops, no, wrong screen. Share screen. Okay, there we go. All right, so I hope you like that. I hope it works well for you as a teaching aid and I'm trying to use that kind of thing when the code starts to seem a little more difficult to understand. And so then we talk about, well, it's a list, so we can actually put a whole bunch of different things in the list, and then we do some applications of that. And I just need to fly by this because I want to get to push buttons before we finish today. So you can modify the way the list is indexed, and And so then an example of that is in blink sequencing. And so let's try this example at the end of blink sequencing. So I want to look for, how it works in blink sequencing. Blink sequencing, how it works. So let's have you guys try this one. And I lost the chat again. All right, here we go. Okay, so download that one. Download that one, and then so copy your link into your Chrome browser. And then download it. Then go back to the Python editor, drag and drop it in. And then make sure you're connected, which it'll show you disconnect. Hit flash and observe what your lights do. It should look something like this, where it's using the list of, we're using a list in this program, the lists that we just introduced. We're using pin 13, pin 14, and pin 15 to go through the entire sequence of pins of lights. And in the assessment materials, there are challenges to set up a stoplight pattern using a list of pins and a list of times.
Andy,
Yes,
mine
is that
is
Rosa?
working. Yeah, that's me, it's Rosa. But
Okay.
it's only working if I press the resistors.
Let's see here. I wonder if it's possible to pin Rosa to the main screen. Okay, Rosa, I've got you zoomed in maximum.
Okay.
Yeah, if you hold it just in front of your, like below your chin is fine. Okay. So yeah, wow, you're holding the resistors down. Now, when you let go, it stops.
Oh,
Sure.
something fell. Yeah, one of them fell. Yeah, one of them fell. Let me
Okay,
go back.
so generally, Rosa, that's going to be, well, actually, the fact that one of them fell out, it might provide confirmation that the legs of the resistor need to go a little bit further into that each leg might need to go a little bit further down into the socket to get a good connection.
Yes. Okay, thank you.
You're welcome. Let's see, I want to unpin you before going back. Remove pin. Okay. And share. Okay. All right, so those are some examples of using lights to get across different things, the concept of frequency, the concept of period, the concept of binary versus analog to digital, adding a separate light, learning about lists, and then applying lists to make as a handy way to make a sequence. So let's see here, 10 minutes. All right, so let's try measuring the light with the voltmeter. Okay, so that one, want to make sure you've got this down. Okay, so I'm going to paste in this chat. Paste. All right, there we go. So measuring the light with the voltmeter, we want to connect your black alligator clip probe to by the blue line here, and then your red alligator clip probe by P13. And
Just to be clear, we're going to undo the one that we started with to
let's
set this
see.
up.
No, thank you for being clear or for requesting clarity. What we're doing here is this is a little bit of a backtrack from this. This is a point on the way of the circuit you set up. So we don't want to take anything off. What we want to do is just leave everything on there that we've got, and then just simply connect the alligator clips in these two positions shown here to P13 and to the rightmost socket by the blue line.
But Andy, do we leave the buttons and
Oh,
all
yes,
the other-
please.
Okay,
And
you see,
normally
that's what I
that's
did.
clear. It's just the fact that I had you guys build everything up so that we weren't stopping to build and troubleshooting our things in between was all.
I get it. Because I actually just took it down and put it like it is in the picture. So
Oh,
that-
goodness.
that mistake.
I am sorry about that. Okay, well, we can stay after to get it rebuilt and just make sure that you've got some of those other things going, because we're going to do push buttons next. And so, so I wanted to have it all built up so that we could just kind of go through some of the code examples without getting stuck. But like I said, we'll just if you have a few minutes to stick with us afterwards, we can make sure that your push buttons are going. But for now, just go ahead and put the probes on P13 and on that blue socket. And then I pasted in the I pasted in the download, the hex download. And now this time, this is what the students do. So it's a little bit different from those things I was sharing with you. All your students are going to do, if they have a pre-written piece of code like this download, is they're going to right click and select Save Link As. And then, put it in the downloads. And it'll appear just like the other downloads you did. And you can go to the Python editor and drag and drop it in there. And then flash it into your microbit. By the way, go ahead.
The drawing.
Okay. On my way back. So it's the alligator clips, the red alligator clip goes on the pins for P2. Black alligator clip goes on the pins that are by P0. And let's see, it is working, showing oscillated voltages of 0 and 2.74 volts. That is exactly the expected, or that is absolutely within the expected range of voltages. It would be nice if it gave us a nice clean 3.3 volts, but that's not in the cards for this microcontroller. Okay, so once you flash it, this is the part that I want you to remember, is after you've flashed it, go to Python, or no, I'm sorry, cyberscope.parallax.com. I'll paste that in a second. There's the Cyberscope site. It also is actually in the instructions. So Rosa, are you okay?
Yeah, I think I had done all of that. And
Okay.
so I'm just trying to figure out like which chart that I did. Right, with those of us who did the checklist did these things, right? Or no?
Yes.
Okay,
Yes.
okay, okay. Thank you so much.
Yeah, it's kind of hard without seeing everybody's faces and without being able to see everybody's kits to know where to start and restart. So I apologize for that if this has been an exercise in repeating it for some of you. I think though, or I'm hoping though that by doing it and talking about some of the items, for example, like on the script and tests page, that you can download it and then open cyberscope.parallax.com. And it's a good idea to click disconnect on your microbit before you click connect on your cyberscope. Another thing is some of you may have more than one serial port. Some of your students may have more than one serial port. So it's a good sign if it says embed serial port. So if you see more than one serial port, like I've got my Bluetooth stuff going on here, then there's the embed serial port on COM52. When we connect to that, it should start giving me some voltmeter data. So there we go. Okay. So now so I take it we did not go through push buttons. Is that correct? That would be the new material?
You had us in the list.
Okay, so we had, okay. Okay, so yeah, I'm showing 2.7 volts and 0 volts. And what I wanted to say about this is that this is a really important lesson for the students to be able to see that on and off voltage next to the light, which is, got to get it so you can see it here, next to the light going on and off. So there it's off, it's 0 volts. There it's on, it's 2.7 volts. And so the idea that it's a programmable way of making the voltage change is reinforced, as opposed to, oh, it just magically went on and off when I used the right method calls. Okay. So is everybody, so you guys have all got the voltage measurements. One thing we could do is well, I think we might as well end the session on the oscilloscope measurements. And then I'll pick up with some of you guys offline. I did not realize that how many of you had gotten through that whole thing. So I apologize for that. So we will keep basically the schematic is the same, but now the script is different. So this is the next activity that the students would be doing. Okay, so there we go. So now what you're going to do is you're going to, first of all, disconnect the cyberscope. Make sure to always only have one thing connected at a time. Okay, then after going to the page and downloading Blink with Plot, after downloading Blink with Plot, then make sure to open it with the python.microbit.org editor, connect, flash, disconnect, and then go over to the Cyberscope. And you should just be able to hit connect again, choose your COM port, and it should automatically respond to your to the new data that's coming to it. So I want to make sure that everybody has this, and I do want to make sure to talk about triggers before we finish. So let me know if you when you're ready to continue. I'll watch the chat here.
Andy, but when we check this, the lights are not supposed to be flashing, right? Or
Oh, they are supposed, yeah, what they're supposed to be doing is the light is supposed to flash with the, I've got two ready.
okay. I only have the green flashing.
And, oh, I'm sorry, yeah, only one light should be flashing. So the script, the script is only flashing the light that's connected to
13.
pin 13.
Okay,
Yeah.
thank you. Okay, thank you. Yeah, I should have looked there.
Okay. I'm hoping that everybody's ready. Just yell out stop if you're not. So the activity that follows the basic one that we did on this page has you, actually I need to refresh my memory on that. Okay, so oscilloscope. So we just did the basic script and tests, I believe. Oh, so we set it to 500 milliseconds per division. So these are important measurement techniques, and so I really want students, and plus it helps give students a connection between graphing and measurement in a nice way. And so so the first thing to do is to set your time per division from 1,000 to 500 milliseconds. And what that does is it zooms in on the high-low signals. Next, we're going to zoom in even further down to 250 milliseconds per division. And that should give us a larger, and now we can, and so we can see an example of when something is on for a quarter of the time in graphing terms. Oh, sorry, that's half the time. I think I had them adjust the code so that it was a quarter of the time. Then finally, do you see how it's kind of marching across the screen? It doesn't really, if we go back to 500, it doesn't necessarily stays put. It moves, the signal moves around a little bit. And so one thing you can do is you can say, all right, I want the signal to always start at a certain point. And so what you can do is this trigger setting down here, you can set to rise. And what'll happen when you do that is a pair of crosshairs appears on the plot. And after about 10 seconds, the plot lines itself up precisely with those crosshairs at the point where the signal is traveling up and passes through the horizontal greenish crosshair and the vertical purple crosshair. And to verify that, you can, for example, drag using the little control that's below the crosshair. You can drag it to the right to drag the crosshair to the right. And each time you do, after 10 seconds or sometimes less, the graph will automatically align itself to the new position that you drag the crosshair to. And so that's trigger, and that's going to be important in later lessons when we're observing things like, say, a servo control signal. Okay, so it is now 2:34. And let's have a little bit of post discussion about things that you're interested in seeing for Friday. Stop share. And then let's see. So does everybody see me, or do they see
A picture of you.
okay, so you've got me. All right. So let's talk
Yeah,
a little bit about
Just the picture, not the camera, just the picture.
Oh, that's
Stop it.
right. Okay, so I need to stop my it'll take a second. I just switched off the document cam feature, and now I'm coming back to the Andy cam feature. Let's see here. Start video. Am I visible yet? Okay, very good. Am I upside down or right side up? Okay, good. All right, folks. So, I was hoping to get to push buttons today. Push buttons is not very much more work. It's a lot quicker than the rest of this material. And then for the next session, I wanted to do some servo applications, and then twisting a potentiometer dial and adding that into the mix. And then we'll talk a little bit about the available curriculum resources for that. We'll have Nicole Litterer. She'll be our guest speaker. She's been working on the standards alignment material and some of the assessment materials that you'll be able to download for this. And she'll talk about what she's been doing with that and be able to answer some of your questions on it. And I guess in concert, we'll show you where to find those things. So that's the plan for Friday. So what I'm going to send you is basically a couple of activities. One, to connect and test your servo motor. It looks like, actually we looked at it earlier, but so it's this little device right here. Is it visible? Can you see it okay? All right. So that gets connected on the breadboard right there, and I will send full instructions on which tutorials or which activities to do, and I'll make it less than I definitely feel like I assigned too much for between Monday and Wednesday, and you have my apologies for that. So we'll have you connect and just make sure your servo is working, and we'll also have you put a little knob to turn on your setup. And then also one last thing will be that you'll be making sure that you can sign in to learn.parallax.com so you can access the assessment materials that are reserved for teachers only. So that's the plan for Friday and the homework for between then, and I'll send you a full email with links and everything. And again, it'll be less than I assigned for today. So how's that sound?
Sounds good, thanks.
All right. Okay, so that concludes the formal presentation part of this. And so now, one thing is we want to make sure that Rosa's got her circuit working okay for next time. And then anything else that you want to bring up afterwards, this will be a open but still microbit related discussion.
So, and remember for Friday, feel free to unmute yourselves and ask any questions, because Andy will be flying solo then, and he may not be able to always see the chat. So if you can just ask, that will be great.
We can.
Yeah,
also-
I only do a few sessions a month. I haven't had a classroom that was remote like many of you have, so I'm not quite as adept at Zoom.
We can always help you. Like one of us can monitor the chat. And
Oh.
that's usually what I do in my classes when I work virtually. If I do not have a co-host, I have a designated student that monitor the chat.
Okay, so Sylvie is the designated help. No, you
Okay,
volunteer.
that's
so-
fine. I'll be here anyway. So.
Well, thank you, Sylvie.
No problem.
That's a great idea, though. I'm gonna
Yeah,
copy
it
that.
certainly is. I will use that on Friday and most likely well after that.
Actually, you're doing great, Andy. I thought you've been doing these virtual sessions. You look like a pro. We're learning a lot.
Oh, I'm so glad to hear that.
We
Because I
are.
have to tell you, yeah, it's usually 1 or 2 months between 3 1.5 hour sessions. And yeah, so it's a little, I still feel like I'm getting used to it. And I kind of want to buy a new camera because I want to get a better image of the light getting dim and bright. I'm hoping that everybody could see that in person, even though it wasn't on the camera.
What I use a document camera. So I have the webcam of the computer and I can disconnect it here. I have like a document camera.
Yes.
And from there, I'm able to show the tabletop and I can switch between webcam and document camera back and forth as I need. And
Okay.
if you have multiple screen, it's a lot. It's like you can logging twice. That's another thing that I do. I have one computer logged in with the webcam, the other computer logged in with the document camera. And depending on what I do, I have one being the main camera or the other accounts. So there's different things you can choose, either swap or have multiple login.
I might try that. So previously I had 2 document cameras and unfortunately it kind of overloaded my computer. So this is one of them.
Oh,
Yeah,
that's it's like that looks like an OCAM type.
See,
Okay.
it's IPVO.
Yeah, mine is OQCAM. Something
Okay.
like that. Yeah.
So what happens with the cameras on LED brightness is, and so incidentally, so I'm actually using one that's almost identical to this currently. And so the 2 things that I learned was, one, when I put a second document cam on, my computer starts to act up, which gets really awkward during the meetings. So that's actually why I was causing this to go blank. And then manually moving it over was just to try to prevent me from winking out from the meeting and taking 5 minutes to get back or something like that, well, because my computer crashed. And then the second thing is that basically that light, when it's doing brightness, for us, we can't see it because it's flashing on and off at 50 times a second. Well, the document cam might be sampling at 50 or 60 times a second, but only taking one of those samples and displaying it. And so we see it all the way on and then all the way off. And so I have not had much luck with a camera to give me the brightness yet. But I'm hoping to find something to get that one across.
Yeah, and
GoPro is now using, they have a webcam beta for Windows, and it's also being used well with Mac devices.
Okay, that might actually be something to try. I'm getting my notes up here.
And the
Okay, so
other
that
thing
was-
is for the LED light is depending on your lighting, they will be more or less obvious. So that's something to fight with how much you see.
Yeah, because
If it's
it
too
might
bright.
be getting a little bit swamped, wouldn't you say?
Yes. You won't see much LED lighting up with that.
Yeah, let's see. Okay, so I'm looking at the chat now. We've got one person signing out. And I guess I guess we're all in agreement then on real quick doing a little push button at the beginning, then doing some servos and some twisting the dial. Is that we're good with that for a Friday thing, and just like basically connecting and getting your servo running is all we'll do for homework, along with, well, connecting and getting the servo running, the dial. It'll be very limited compared to this homework session.
The other thing I sent you
sorry.
an email because there was a typo in one of the solution script. So
I saw it.
Yeah, it's
Yes.
just spacing, and you do one run that I realized, oh, that's alignment. It's actually good because that makes the students look for why is it not working.
Yeah.
But on the other hand, was that really your purpose?
Yeah, no, the purpose was not to facilitate a learning to debug experience at that point. Yeah, so thank you so much for sending that. I'll forward it to Stephanie and she'll go ahead and fix that one. And then there was somebody else who started to say something.
Sorry.
Oh, that was
No
me.
problem.
So I actually appreciate more homework, so that saves more time. I'm not a freak or a nerd. I just I appreciate more time during the live session where you can actually spend more time explaining things instead of us doing the hands-on work that we could have done before class. I don't know
Gotcha.
if that's just my opinion or
Well, it's what I was trying basically to accomplish in terms of you know, the handwork is I agree with you completely, and so that's my hope, is that this works okay as a format for everybody. And yeah, it would be my preference too, because I want to be able to kind of like get the circuits built in a more leisurely fashion. And another thing is like looking down when you're building the circuit and then trying to look up and follow me. That's been one of my biggest, oh boy, I just lost sync with the audience, because, and then also somebody will end up having a circuit that they can't get to work. And so in the larger events, yeah, sure, we do have little sub rooms where they can go, and there's also an extra helper. But you know, with a group of you know 20 like we've got today, it wouldn't be so bad. But with the larger groups, it definitely does derail things. So yeah, I'm in full agreement there.
Plus also it's the difference between a training workshop to use the material and a teaching workshop where you're actually teaching the content.
Mhm.
There you're more like training us, giving us the tools, giving us tips. So it's more like, the point is not teaching us electronic, it's showing us how to use what you provided and giving us tips with that. So it's more of a training than the teaching.
Yes, yeah, and that is also the intent, is just a training workshop as opposed to a teaching workshop. I don't want to be telling you guys a particular teaching approach for sure. Yeah, and
Ohm's laws, right?
I'm sorry.
Let's review Ohm's laws.
Yeah, exactly. Yeah, so this, hopefully now it's kind of clear that this has at the beginning of a given chapter the basics, and then it gets deeper and deeper as you go in, and by the end of the chapter you've got your voltmeter and your oscilloscope measurements, and salted in there is also some math to say, okay, well, you just took a voltmeter. I actually forgot to mention that, but yeah, when you were taking voltmeter measurements, there was a point where it was all stop. You know Ohm's law now, so you don't have to pull the circuit apart to get the current. You can probe across the resistor, you can plug those numbers into Ohm's law, and you can figure out the current, and it's, you know, it's just about as fast. And so so those kind of things, it's got a little bit more than I've seen of it. Well, it's got a lot more in many cases than I've seen available. There's quite the plethora of let's get excited and let's have some fun doing something that's very lighthearted. And then there's a little bit of extra and deeper stuff. And well, actually the CyberBot robot, which I'll also talk about briefly on Friday, does allow for a deeper dive as well. And let's see, but yeah, so this is trying to fill a void that's been created by everybody that's publishing about this. Seems to be kind of drifting away from the challenging material, you know, from doing it's like math is sort of a thing. Doing calculations is often a wait, why did you put those in there? We're supposed to be, you know, just having an experience, and there's a ton of need for that. Yes, I agree. But what I, again, was seeing was that it seemed like there was kind of a vacuum of getting the actual curricular checkboxes for many of these things checked off. And so that's the resource that I'm trying to build for you guys.
And there's quite a few hours of teaching and practicing to do for the students there. So it can be extended to a full quarter, depending on what we do or more.
Yes, yeah, I agree. I agree completely.
And I'm glad you get to the depths of the material, because it really helps students understand, you know. And I also agree with what the other person said. I really like the homework, and I like what we do in class, and you go in depth and show us like tips and all of that. I was just mentioning that it felt like a lot.
Yeah.
For just, you know, one day in between and everything else that's going on. Does that make sense? I mean,
it totally makes sense, because it matches what I was feeling in my stomach as I was typing out the instructions.
Yes. So it was like I finished it like minutes before the class, and I wasn't spending a bit of time. But I mean, it's just I had other things also going on.
Yeah, no,
but I do like what we get to do at class, and I like to be able to do that on my own, because you know, I found out my little mistakes, which, by the way, is this. I just set it back to what it was before.
Oh, good.
Is this
Excellent.
what it's supposed to look like? Okay.
Yeah. So would you like to try? Let's run a quick test on that. And then anybody who's still with us. Oh, is that Sylvie waving goodbye? Bye-bye. Okay. Oh, or are you telling me you can see yourselves? Okay, here, I'm going to share the screen real quick. All right, so for anyone who's still left, let's go to the push buttons. We might be repeating this on Friday. But let's do 2-button control.
So Andy, do you want to continue recording, or you prefer to have the fresh on Friday?
You know, I think I want to continue, and my rationale is just that, hey, we can have this material at the end of this one.
Yep.
And for those who have YouTube, if they feel like they're repeating it, they can just kind of drag the little time control.
It's at the end, so the class is already done. So
yeah. So this is not anything I'll be expecting folks to know on, or to have, because I do plan to repeat it on Friday. Okay, so here's the link to some test code for that. Remember, everyone, to disconnect your cyberscope. Make sure to hit disconnect on your cyberscope. And then you can connect on your microbit editor.
Why is that, Andy?
Well, it's okay. I think what's happening here is that, all right, I still have the cyberscope script running, I hope. Okay, I just went to the serial terminal. So where we did little hello messages and countdowns and stuff. Do you see how this information is going through here? So we're seeing actually voltage information as it is sent to the cyberscope. So it's saying that the Y, Y value 2, that's the P2 probe, you can see it alternating hopefully between 2.69 and 0. And then you can see the X timestamp. And so that is the actual data that is being sent to the cyberscope. Now, if I leave it connected, so right now it is serial connected, the serial terminal is connected. And if we go to the cyberscope and try to connect it, I'm going to get an error, I think. It didn't give me an error, but it is definitely not plotting. Okay, so something's not working here. And let's see what happens if I go back to the editor. The editor also isn't doing so hot either. Do you see how it's just kind of floundering down here? Okay, so now if I disconnect the editor and go back to Cyberscope, disconnect and reconnect. Yeah, I actually managed to make it kind of unhappy. So what I'm going to do is hit the refresh button and then connect again. No, not that one, that one. And now we're back. And so the idea is that there are two ways to display this data. One is resident to the microbit editor, and then the other is resident to the cyberscope, but they can't both be connected to that same data stream at once. And so that's why I try to get everybody in the habit of disconnecting in one, then coming back and connecting in the other. So we're disconnected there, we're connected here, and then we had, now we have the master button test, I would say. And we can flash that.
Oh, you want me to do that?
Oh, yeah.
Okay. So that's the one you linked?
Yes.
Okay. I think I already have that. Buttons make LED rotate. Maybe not.
Okay.
I don't know.
Is the LED sequence going downward right now?
And I don't know. Hold on. I'm trying to. Yeah. No, I'm not.
Just go ahead and do your thing then. So
Yeah.
basically, on for folks who might be watching on YouTube later, if I press one button, I get one sequence of lights. And then when I press the other button, I get a sequence of all three lights in the reverse direction. And this is basically just a script that allows us to test both buttons and all three lights.
So now I just run it, correct?
Mm-hmm. And then press and hold one or the other button. And you want to see the lights go in, all three lights go on and off. Well, basically, like if you press the bottom button, you might see the red go on and off, then the yellow go on and off, then the green go on and off, then red, yellow, green again. If you press the upper push button, you'll see green, yellow, red, green, yellow, red.
Can I show you?
Yeah. Okay, so that's frozen on one, huh? Okay, now,
It was working. I don't know what happened.
Try
Okay.
Oh, perfect.
There.
Okay. Oh, how funny.
It's when I move it. Yeah.
Yeah. Something is, okay, that looks good. That looks great.
Okay.
Can you hold it back up again?
Sure.
Okay,
I
I'm gonna
don't know.
take a
Maybe
screenshot.
it's, I don't type things, you know. See, it's froze when I put it like that. Oops, now it's okay. There, now it's working, but when I put it, oh, there, it's staying. Yeah, it's working.
Yeah, perfect.
It might just be like you said, I don't have something. When I press down the leader, oh, how do you call them? I forget.
Resistors?
Like resistors, like you told me, yeah, it worked fine. So I press the other button and it should do the same, right?
Well, so one button will make the sequence go from top to bottom. And the
Okay,
other button will make the sequence go from bottom to top.
okay. Oh my, this is really, I'm dyslexic, so that's really confusing for me. Look, is this what you expect?
Yeah, so I expect
And then
it
the other one would
is
be,
the other direction. Yes,
is it
perfect.
working?
Yes, yeah, so,
Okay.
yeah, I get the dyslexia thing. So hopefully if you hold one button, it'll be
Yeah.
apparent that the pattern is traveling
Yeah,
in
I
one
see it
direction.
now. Yeah, I
Okay.
have to see those things. I just have to spend a little more time. Most people,
Yeah.
I eventually see it.
Yep.
Okay, so I have it, and this is how you want me to have it for the next session.
Yes, except for I will be
Okay, like
sending
this.
an email to connect some extra things.
Oh, okay, I see. Okay, you know what else I learned when I did the buttons by myself? Like, you really have to curve it, like you said in the illustration.
Oh yeah, bending the ends of the resistors,
Yeah,
yes.
because I took a shortcut on the first one, I did it, but on the second one, I'm like, that looks like it will just be fine.
Yeah.
It wasn't. So I paid my
Actually,
price.
yeah, I did the same thing. I was
Yeah.
building it. So I had that master set that I just
Yeah.
held in front of the screen. So this is
Yeah.
basically the one I've been writing with. So that, you know, when I do
Yes.
the tutorials, I've been using this for
Yeah.
quite a while.
Yes.
And the idea is that as they go through the chapters, they add the lights, then they add the push buttons
Yes.
and so on. And so now we've added the servo, and then there should be a potentiometer right down there, a little white
Yeah.
doohickey
And then
gizmo.
you said this whole thing is supposed to take 40 hours. That's what I remember.
Well, that's an estimate, but
Okay.
I'm looking at it now, and I'm thinking it may end up going over 40 hours.
Yeah. Oh, okay. Okay. Then the other thing is I broke one of these black things.
Okay.
The cable, is that okay? I won't need it. There was a reason.
So it was just one of the wires.
Yeah, one of the wires. Yeah, the end.
Okay,
I pressed
yeah,
it so hard.
that's fine. You've got plenty.
Yeah, okay, good. Yeah,
Yeah.
I know I still have a bunch, but I was wondering if on Friday. Then with the resistors, I saw that in the, like when they go very far, you suggest that it's straight and then bend.
Yes.
Do I use the tweezers for that bending? Because I found I'm very paranoid about things being straight. And those resistors drive me crazy.
Well,
how do people usually bend those so you can keep them straight? Mine look like worms by now.
yeah, so I just bent these with my fingertips.
Yeah.
Is it
okay.
visible?
Yeah, I see it. That's better than mine.
Okay.
Yeah.
Basically, I just put my thumbnail, you know, when I bend it, I have my thumbnail as the part to kind of make it crease.
Okay. Okay, great. Wonderful.
A tweezers or a needle nose pliers are perfectly fine. Yeah. Although that tweezers might be a little bit delicate for what you're doing, but or not. Actually, no. Yeah, it depends on how you hold it. If you hold it through, like if you hold it with the very tips of the tweezers, the tweezer will be having difficulty. But if you pinch, you know, further up, like there's a part where the silver transitions to black at the tip.
Yes.
Okay, so if you squeeze it right where it starts to be black, if you put a resistor in there, you can actually put the tip of the resistor in, squeeze it closed, and then bend the resistor. But like I said, just simply using
Yeah.
your thumb nail to make the
Uh-huh.
corner is perfectly fine.
Okay. Okay. So I will do that. Thank
All
you so
right.
much. I'm learning a lot, but I feel it's a lot of information.
Uh-huh.
So we're supposed to, like, maybe after we finish the training, go back and review it to digest.
Oh, absolutely. Yeah,
type of thing.
the tools, I'm just mainly trying to give you the tools you can
Yes.
use to go through it at whatever level you feel. So some teachers will actually be going through it maybe 1 or 2 activities ahead of their students.
Yes, yes.
and then other teachers will be going through it during the rest of this semester before they teach it to their students next semester. So it's really going to vary, but you'll be needing to stay ahead of your students in one way or
Yes.
another and go
Yes.
over it. And my main thing is to get you started, to help
Mhm.
to make sure that all the tools are fairly familiar, and
Yes.
and that knowing, also just simply knowing that the instructions that the students are getting are doable.
Yes.
You know, but by you following some of the student instruction sets, it helps just everybody who has to teach it gain the understanding that, yeah, I can tell the students, I can assign them, you know, this activity or these 3 activities or whatever. And then, you know, okay, kids, go to lab, and then we'll talk about it, or, you know, so you can be thinking about what your approach would be by experiencing some of the same worksheets that the students are going through.
Much, and
Oh,
I
my
really
pleasure.
appreciate it. This is fun. I'm
Okay,
gonna
well, very good.
re-energize for the next one. Thank you.
Okay, my
Great
pleasure.
day.
All right, and then
Thank
I'm
you,
trying to,
and that concludes the class for today.
all righty.